Hello, I am Neeraj. Today we will discuss on a very important topic related to large language model and transformer. Several times what happens, we say that when we provide or when we feed our large language models with a very large input, very longer sequence lengths, then it doesn't provide a very good information or very good output. So why it happens? Or suppose we try to solve this problem, then how we can solve? Someone say that we can divide our text into chunks. We can do some topic-based divisions. We can use some knowledge graph or knowledge hypergraph and then do some kind of prompt engineering to solve this problem. But whatever you do, either it will require a lot of efforts or you will lose the continuity in the text, continuity in the output. So one thing is like instead of doing some external patch-ups, whether can we think to do something new at the transformer training level so that we can train on a smaller length sequences and we can test on a higher length sequences. So a lot of paper published in these directions, like how we can do that. But what is the reason why old or vanilla transformer that is discussed in attention all unit paper is not able to do such kind of things? We already know that a lot of deep learning architecture like LSTM, CNN, traditional perceptron models generally show some inductive biases. To solve those kind of inductive biases, transformer came up with some concepts of positional encoding and attention-based mechanism. They combine it effectively to get a very good result. And that's why transformer is like king of everything. But the positional encoding that actually proposed in that original old paper is the main thing or main thing which actually affects that kind of extrapolation. So extrapolation here, like we want to test, suppose we want to test in a sequence of length 1024 and we want to test in a higher length sequences like 2048 or higher, like that. So that kind of extrapolations, why the current architecture is not supporting. So in the current architecture, means old attention all unit kind of architecture, what they did, they applied a sine and cosine based positional encoding. So what is this positional encoding? Suppose you have a text like hello, how are you? And suppose another hello comes here at some fourth position. So in that case, the traditional embedding, word embedding will fail to differentiate between this hello and this hello. And you will face the problem. So transformer applied the positional embedding. In the positional embedding, you can see that the simplest way to do the positional embedding is to use the index like 0, 1, 2, 3 index position. But it generally, if you just increase to a very higher length sequences, then such kind of index-based positional encoding actually lose the semantics or in the time of computation. So the paper attention all you need actually proposed a sine and cosine based positional encoding. The favorable facts given with this is like sine and cosine are periodic functions. We can do some level of extrapolations with such kind of arrangements compared to the numeric system like number-based indexings. So with this position, you will find that how it affects the entire computation. So earlier we were just using the embeddings. Like suppose we have word like hello, how are you? We take each of those words, we calculate the embedding of each of those words. But with those embedding, we calculate the sine and cosine based positional encoding also. To calculate the positional encoding, now here we assume that our embedding dimension is just 4. That's why we took that 4 array of vector of length 4 to put our embeddings. So we put some, suppose it is like 0.0, 0.8, 0.6, 0.3, 0.7, like that we got some, 0.8, 0.7, right? We got some embedding. And after that we will calculate the positional embedding. Now for all even embedding dimensions, we will use sign-based positional embedding. We will use the sign function to compute the positional encoding, and all the embedding dimension, if the value is odd, we will use cosine function. So here, first case, our position is 0. So you can see the index position is 0. And so we have 4 embedding dimension for 0, 1, 2 and 3. So for 0 embedding dimension, when we put all those value here, we will get value 0. So we put value 0 here. Similarly for second embedding dimension, we will get value 1, we put here. And similarly here, we will get 0. And for third embedding dimension, we get value 1. So here 1. Now, the final value that will be, which will go for will be like 0.1.6, 0.8, 1.7, like that. So this will totally different. Similarly, for second position, so position equal to 1 and embedding dimension 0, 1, 2, 3. For embedding dimension 0 and 2, we will pass the value 1 and 0 to the sign function, and when we pass the value of 1 and 0 to the sign function, it gives the output of 0.8410. And for embedding dimension 2, again we will use the sign function, and this will give this output. And for odd embedding dimension, we will, for first and third, we will get this embedding dimension output. So this will be the positional encoding. Instead of 0, 1, 2, 3, 4, this will represent the positional encoding with respect to the embedding dimension. So here we will add this with their actual embedding dimensions. So the how, which comes at the first positions, suppose this comes at some another position, its total embedding will be totally different from this how. So now this is the actual culprit. So in the current scenario, the sine and cosine based positional encoding system actually creates some issues, and due to that we cannot extrapolate to a very higher length. So in that case, what we can do and how it affects the everything, entire scenario, like how, for example, when we take the data after positional encoding, we pass it through the attention layer. So the transformer contains the multi-head attention layer. Now the next part is to use this positional embedding plus embedding based final embedding for the transformer and pass it through the softmax function, pass it through the attention layer. So this is the main thing. And next we will show that at the same attention layer, how the proposed paper proposes some changes, means avoid the situations where we cannot test our system to a very higher length sequences with respect to the sequence length we used for training. So let us try to understand. So in that case, suppose we consider our embedding dimension as we discussed, we are taking just 4, and we have forward sequences like hello, how are you? We are considering hello as a key 1, then key 2, key 3 and key 4, representing again queries like Q1, Q2, Q3, hello Q1, and then Q2, and then Q3, and then Q4. So in that case, how attention actually works. So in that case, we will take our keys, key 1, key 2, key 3, and key 4. And then we will use here our queries. And then we try to get some similarity score between query and queue. So for that, you will get like that. So in that case, this is actually calculates the cosine similarity between queries and keys. So here also we have a vector of 4 words like Q1, Q2, Q3 and Q4 like discussed here. So here also it will be a vector. So in that case, based on the cosine similarity score, suppose we get some score like 2.7, 3.1, 3.3, 3.0, 3.9, 3.9, and then 3.0, 2.1, 2.3, 2.0, 2.1. Just so now you can see that these scores these scores are high. So generally we normalize it or we scale it by dividing it with the dimension of root under dimension of keys. So here our dimension is like 4. So based on that we will normalize it. And after the normalization, it may be some value like something smaller value will be there. And after that normalization, suppose we apply the mask operation, but here for the encoder value, for encoder architecture, we are not using the mask attention. We are not using the masking part. Now the next part is softmax. So suppose here our S dash S1, S dash S2, S dash S3 and S dash S4 is the normalized similarity scores. That is here. So S dash 1 is representing this. Suppose after division we got this score like 1.3 and something. So suppose we improved all the scores and now it is representing that S dash 2, S dash 3, S. Now the next part is to compute the softmax score. So softmax score computation is so this computation you can easily understand. This is like a query and key transpose, and after that we did the scaling also. Till here we did the scaling also, and after that we compute the softmax here. So this will give the softmax score. So again the 4 scores will be there. It will show that with which word it is more similar. So the softmax score generally helps us in getting the information like which word is highly similar and which word is less similar. And generally softmax increase the differences between those similarities. So that's why it plays a very important role. So now here the problem is like we use the cosine similarity sign and cos based similarity to represent so here we use the sine and cos based periodic functions as a positional embedding to change the actual embedding of the word. And this is the actual problem here, because when we use such kind of encoding and when we change the word's actual embedding, then after a certain limits it is very tough to extrapolate this. So in that case some papers actually solve this problem by using the attention with linear biases. Means they remove this positional embedding related attention. They remove all those attentions.